Now I stop right there because if you look up at this picture, here's where I'm going to cut the truss, right? Just like this. So that's it. That's all I want to draw. And I know that whatever forces are here, here, and here, and they have to act along these directions, the direction of the member itself, they have to hold this all in equilibrium. So everything has to be held in equilibrium. So I can do that. I can either anticipate which direction they're going to be, or just draw them all positive and work from there. So one of the big differences between the method of sections, which I'm showing you now, and the method of joints. In the method of joints, we look at the free body diagram of the pin. We focus on the pins. Here, we're out in the middle of each of these members, and that's what we're focusing on. So I could just put my arrows like this. This would be my force in BD. I could look at this one going this direction. This would be the force in CD. And I could draw this way. And that would be the force in CE. Now, you can draw them any way. I could draw them all positive, all negative, whatever. But here's why I drew them in the way I did. The only one of these three that acts up and down, the only one of these three that acts up and down is CD, right? BD is horizontal and CE. So, and I know there has to be a downward force because there's an upward force of 7 kilonewtons here. So I know the downward component of CD has to be 7 kilonewtons down. So that's why I've drawn this down, and then I just keep that reasoning going. If CD also, if it's acting downward, it's also pushing off to the left, right? So there's no other, this external force isn't pushing left or right, it's up and down. So these, the combination of them have to offset that leftward force. So I just drew them like I did. If I'm wrong when I do the algebra, it'll come out as negative, and I'll know I'll have to turn those arrows around. So so the next step then, I'm going to sum the forces in the y direction have to be 0. And again, I'm just looking at this one now. So the only two in the y direction are CD times the cosine of 45, because of the way these are set up, the horizontal and vertical members are 4 meters and 4 meters. So these are 45-degree angles. So this is a 45-degree angle. So CD cosine 45 is my up CD in the y direction. So when I sum this, I've got 7 kilonewtons up minus CD cosine 45, that has to be 0. So when I solve that, CD is 9.89 kilonewtons. And I guess I'll just leave it like that for now, and we'll come back to figure out whether I say this is compression or tension. You might be able to see it's compression, again, because I'm pushing on this member. I'm looking at the free body diagram on the member, and it's squeezing it. So that's compression. In other words, since this came out positive, I've drawn this arrow correctly, and that arrow indicates compression. So the next thing I'm going to do is sum the moments. I can pick any point, right? No matter where I pick. What I'm going to do here is pick this point at C, because if I pick that point, this goes right through it, and this goes, the line of action from this member goes right through that point, so does this one. So now I've just got two other forces causing to rotate about C, and only one of those is unknown. So by choosing C, some of the moments about C equals 0, I can isolate that unknown and find it. So my equation here, move this up a little bit, will be BD, and its lever arm is 4 meters, and that is a positive, using the right hand rule, that's a positive rotation. So it's BD times 4, and then about C, this 7 kilonewton force is clockwise, that's using the right hand rule, that's negative, so it's 7 kilonewtons times 4. And that equals 0. So solving that, BD, the force in BD is 7 kilonewtons. And that was one of the things I wanted to find. So now I can find the force in CE. And I'm going to do that by summing the forces in x direction. I think I have enough room. I can just keep doing it right here. So summing the forces in the x direction equals 0. I've got this 7 kilonewton force is just up and down. It doesn't push left or right. So I've got CD times the cosine of 45 acting to the left. I've got BD, and this came out positive, so it's also, I've drawn that one right, it's acting to the left. So CE has to be the way I've got it drawn here, and we can figure out what that is by just solving this equation, some of the forces in the x direction. So I've got negative BD, which is 7, so negative 7 kilonewtons, negative because it's going to the left. I've got negative 9.89, because that's the force in CD we found up here, times the cosine of 45 degrees, plus CE equals 0. And the reason I have CE, because it's right here, right? And I've got that drawn in the positive x direction, so I wrote it as positive. So now I've got an equation with only one unknown, so I can solve for it. So CE is equal to 14 kilonewtons. And that's the other thing I was supposed to find. So those are my two answers. Now the question is, what does this mean? Well, again, I'm looking at the member, so I'm CE, think of it pulling on this, think of this as like a rubber band, right? And I'm pulling on it, so it's in tension. Here I'm pushing on it, so this is compression. Up here for BD I'm pushing, so that's compression. So BD is in compression, CE is in tension. And this is going to become important because some materials are better in compression than tension. So when we look at mechanics of materials, it's really important to recognize this. Okay, so there's an example of method of sections.